Good afternoon to you, my students. You're welcome to this lesson. Once again, it's me, your teacher, Ojambo Joe, and we are here to continue serving the nation. And as you know, it is at this time that we're supposed to continue following the Ministry of Health guidelines. Let us keep sanitizing, let us keep washing our hands and stay out of danger. In case you are supposed to move out of home, please endeavor to put on a mask. So, like we said, if you remember in our previous lesson, when we ended the lesson, I left some assignment, and as I promised, we would start from that point. So it is at that point that I want us to begin our lesson from by trying to go through that number which I left. If you remember, people who had written the question, I'll draw the circuit arrangement. This was our C1. Somewhere here, we had a capacitor C2, and we had a DC source, which had 90 volts, and that is DC. Then at this extreme end, we had another capacitor, which we called C3. And we were told that C1 is 14 microfarads, C2 is 30 microfarads, and C3 is 20 microfarads. Because the question said in the diagram below, C1, C2, and C3 are capacitors of capacitances 40 microfarads, 30 microfarads, and 20 microfarads respectively, with air as the dielectric. Stored. Okay, the energy stored in our system. Because the question says, calculate the energy stored in the circuit when all the capacitors are fully charged. So, and if you remember, our last lesson was so our energy stored. It is now time to mark ourselves, and we went off, and those who could have done it correctly, you would still be able to mark yourselves. So we said, if you remember, we said that C1 and C3, if we covered these two, if we covered the DC source and the capacitor C2, you realize that these two are connected across each other, so they are in parallel. And from our capacitor networks, we discovered that C1 is in parallel with C3. And when two capacitors are in parallel, what did we say? We get the capacitance as two capacitors. It is given as C1 plus C3, which means C13, if I'm to denote it like that, will be C1 is 40 plus C3 is 20. When you add those two, C13 gives us 60 microfarads. So having got this, we now discover that our circuit arrangement. Let me draw something here so that we can be able to see what I am talking about. We find ourselves having something like this. This is C13. This is our DC source. So when you look at it, because like ends are not joined over each other, and when we have capacitors in series, two of them, we say that the total capacitance is given by the ratio of the product of the capacitors, the capacitances to the sum of the capacitances. So that means this is going to be C13, our total capacitance C will then be equal to C13 times C2 divided by C13 plus C2. When you substitute into the formula, you will have total capacitance C will now be equal to 3 gave us 60, so it will be 60 plus, beg your pardon, 60 times C2 is 30, then divide by 60, which is C13 plus 30. This is therefore going to become 1,800 divided by 90. So total capacitance is this 0, we cancel with that. Then 18 divided by 9 gives us 2. So this is going to be 20 microfarads. Now, having got 20 microfarads, my dear students, we then can be able to go ahead. Now we have the total capacitance and the total PD. So using our expression of energy stored equal to a half CV squared, we shall then have a half times 20 microfarads. So we change it to farads, divide by 10 power 6. That's why I'm multiplying here by 10 power negative 6 times our PD is 90 volts. 90 squared. The teacher, when you multiply through and divide, we shall end up with, I carried my calc. I work out, even people that say I know are working out, so that we can ensure we have the same result. And multiplication and division has given me an answer which is 0.081. Now, we are talking about energy stored. And from our basic knowledge, we know energy is measured in joules. So don't forget the SI units. So that means the energy stored when we have this kind of arrangement is 0.081 joules. Okay, now that is Roman 1. Roman 2 says the change in energy stored. Roman 2. Change in energy stored. Change in energy stored in the capacitors. In the capacitors, if the space between the plates of C2, if the space between the plates of C2 is now filled with an insulator of the electric constant 3. Of the electric constant 3. So, this is the question. And the only difference we have from what we had in the beginning class is, we are telling us, because remember in the beginning we were told that the space between all the capacitor plates is air. But this time, they have now gone ahead and filled this with the dielectric. And it has the electric constant 3. So that means the capacitance here will change. If you remember the relationship between relative permittivity and the capacitance, we said it is the ratio of the capacitance of a capacitor filled with a dielectric to the capacitance of the capacitor when the space between its plates is a vacuum. So that means, having filled the space with the dielectric, we are looking for C, which is therefore going to be C is equal to our dielectric. The capacitance, when the space between the plates is a vacuum, was given as 30, which means here I'll have 30. So C2 prime therefore becomes 90 microfarads. That is the new thing we are discovering. However, you realize that everything else remains the same. And we had already discovered that the capacitors C1 and C2 are in parallel. So the other one doesn't change. So we can right away go ahead and find the total capacitance. Will then be equal to the new capacitance C2 is 90. The effective of 1 and 3 will remain the same because nothing has been changed. So it will be by 90 plus. This is going to give us, when we multiply and divide, 90 times 60 is 5,400. Divide by, that gives, I have got 36 farads. I hope everyone else has got the same. So that is our new total capacitance. So we can now get this capacitance formula. I can call it now E1. Energy E1 will now be equal to a half CV squared. Remember, it is the same PD supply, isn't it, so class? Therefore, it is going to be a half times 36 exponent negative 6 times 90 squared. What does this give? 0.5 times 36 exponent negative 6 times 90 squared. I have got let me check here. I hope we have not erred anywhere. Is 3 years. Okay. So when we work through, this is 90 times this is 90, that times this is 90, bring it here. The other one was 60 years. Okay, I think we are spot on. This is 5400 divided by 150. 36, okay? 36 negative times I have got 0.14 58 joules. That is what I have come up with. I hope we are on the right track. And having got that as our new energy, the question wants us to find the change in energy. So how do you find that change in energy? You're going to subtract the smaller energy from the bigger energy. And when you do that, it will mean when you compare the two energies, you discover that energy E1, when you find the difference, it will give us the energy. I think form of a review. Now, today's lesson then takes us to the, we can now be able to look at the objectives of today's lesson. And today's lesson has basically one objective, and that is, the lesson objective today is, we want to see how we can be able to work with the connected capacitors. So here we are looking at connections of charged capacitors. Of charged what? Capacitors. So that is our lesson objective. After we have charged capacitors, we can have them isolated. And when you isolate them, you can go ahead and connect them. Connect one which is charged to a certain PD with another one which is also charged to a certain PD, and then see how it works. So we can say, suppose 2 or more capacitors are charged independently, or you can say separately, comma, after you have charged them independently, you isolate them, and then later isolate them and then connected. The connections can be in 2 ways. The connections, and what are those 2 ways? Those 2 ways are, if the connections are such that the like terminals are joined together. Now, when you join like terminals, it therefore means you're putting them in parallel. Join together, i.e., in parallel. Okay? If the connections are such that the like terminals are joined together, i.e., are in parallel, okay? Charge will flow from a capacitor with higher PD, where PD is the voltage or potential difference, to a capacitor with of lower PD until charge will flow from that capacitor which has a higher PD to one which has a lower PD until their common PD is the same. Until their common PD is the same. Until their common PD is the same. Okay, this is what I'm talking about. You imagine you have this capacitor. This is a positive terminal, this is a negative terminal. Then you also have this other capacitor. This is negative, this is positive. So you connect them. Having connected them together like that, charge will flow. Suppose this one here, C1, and this is C2. Suppose C1 has a greater PD compared to C2. That means charge will flow from here to here. And now that is going to happen until the PD across the two is the same. Suppose the PD between them is what? Excuse me, that's what we're trying to mean by the charge moving until their common PD is what? It's the same. One case. We can also have a connection where the unlike terminals are connected together. Now, if the connection is such that unlike terminals are connected together, connected or joined together, i.e. in series. You have all seen a train, it has those wagons. That is the series, are connected with unlike terminals together, i.e. in series. The capacitors share the capacitors do what? Share the charge until the quantity of charge on each of them, on each capacitor, okay? So you can see this is what we're having. Now, one thing we shall find which is going to be different from all the other cases is, much as speed is the same, charge is the same, energy, however, the energy stored okay.
Yeah. When you are ready, let me know. You're wasting our time, okay?
Right.
Finish. Stand by. Stand by.
Yes.
Are you on standby?
Yes.
You didn't see yourself. Stand.
You know Parliament disorganized that.
Okay.
There has been Parliament line.
Yeah, I saw.
So now,